Hi everybody. Just going over this booklet with you guys. It was our fifth inquiry question for the waves and thermodynamics topic. Now we're studying our new topic, term 2. Now there's word in the pipeline that we potentially will be start coming back to school maybe one day a week, week 2, and possibly increasing after that, which will be a welcome for us, since our assignment this term is going to be about it's going to be a practical investigation, and we really need to be there. So keep your eyes tuned and keep your ears tuned and see how we go with that. Okay, let's get into this. So, okay, yes, this was our last inquiry question. It had to do with thermodynamics. So let's have, what I want to do is go over the content quickly and then get to the questions. Now, I left this one strategically last because the content just seems to fall in place, and it's a lot of principles that we've already covered in year 10 and a little bit in year 8 as well. So everything should just kind of flow. It's just adding the mathematics to this that gets a bit complicated. Now, again, most booklets have glossaries, so make sure you're paying attention to those glossaries. If you're not understanding something, maybe you'll find the information that you're missing in that glossary. Okay. So first thing is first is this. It all starts off with this. So it's this idea that we treat all atoms that make up matter as little balls. We call this the kinetic particle model of matter. And what it's saying is that these atoms that we treat as balls, we call them as particles. And what happens is we treat them as if they hit surfaces and hit each other with perfect elasticity. So it means all energy is conserved. So if a ball hits another ball, the amount of energy that is transferred to the other ball is either equal to the entire energy or some kind of a division between the energy of the balls bouncing away from each other. We'll talk more about elastic and inelastic collisions next term, but that's one of the conditions that the kinetic particle model deals with. And what happens is when those particles are some kind of distance away from each other, they're said to have a certain energy, an ability to come towards each other and hit each other with a certain amount of energy. So that's this concept here of potential energy that connects the particles. Yes, and also because we're treating these as complete atoms, but when you do bring those atoms together, there's a certain repulsion against them. And what happens is that is also a form of potential energy. Okay. Now, if kinetic energy has to deal with the motion or the movement of the particles in a particular substance, so in a solid, you can see they're more compacted together. In a liquid, they're slightly further apart, and in a gas, they're completely far apart. Look at the amount of movement that's occurring in that one. So what happens is that is kinetic energy. Now, with potential energy, it's a bit different because there's something going on here. So it's the potential to do work. So the potential to have those particles come back and hit each other, right? There's always two types of energy, which we'll cover this term in more detail, and that they either fall into the category of kinetic energy, which is associated with movement, or potential energy, which is energy that is stored up ready to be used. So think about springs, elastic bands, somebody standing on top of a canyon. All those things are a form of potential energy. And what happens is when you sum all the kinetic and potential energy in a substance or particles, then that's equal to the total internal energy. Okay, move on. Now, what I want you guys to start thinking about is how do we define temperature And this is what temperature means. So temperature is the average measure of kinetic energy of particles in a substance. So, I mean, that kind of makes sense. Now, we've talked about previously how if you heat, say ice, it slowly becomes a liquid. And if you keep on heating that liquid, it becomes a gas. So you can see those particles are gaining the energy that you're giving to them in the form of heat. Heat is a form of energy. Heat is a form of kinetic energy. So you're giving that kinetic energy to the particles. That kinetic energy is being taken by the particles and it's giving them kinetic energy and also potential energy. They're moving further away from each other. They're jiggling much more until they escape the vessel in the form of gas. So temperature is that. Temperature is just the it's not the average energy, average potential energy. It does not consider that. It considers the amount of movement of those particles, and that's just got to do with pressure. That's beyond the scope of this particular course, but it has to do with pressure. So as you heat particles up, that pressure inside, so if you heat particles up inside some kind of vessel or balloon, those particles increase pressure, and by definition, that increase in pressure is an increase in kinetic energy, and because of that, we can relate that to temperature. This graph tries to illustrate that. So you can see as you cool down something, so we'll start off here. As we cool down something, the average is given by this point here, right in the middle. And what happens is that average attempts to consider, sorry, that is not the average. The average is this point here. The average tries to consider the distribution of the particles. So you can see y-axis is the particle. Considers the amount of particles all the way spanning from this side between this middle point that way, and it resolves these particles on this side of the graph. So what happens is at this point, that is the temperature, which is the average amount of kinetic energy by all particles. So you can see all the particles are distributed underneath that curve, and what happens is the most middle point of that curve, when you consider all the particles distributed, is the average kinetic energy, right? And you can see on the x-axis, it's both kinetic energy and temperature. And you can see as you heat it up, those particles start shifting towards the right? Because what happens is they're getting more kinetic energy. If you keep on heating that, more of these curve gets pushed over to this side, and you get an increase of particles going this way. Now there is a limit. You can't get particles to continue to heat up. At some point, they're going to start to break apart. But that's beyond the scope of the 11 course. Anyways, let's move on. We're good here. Okay, let's go into the laws of thermodynamics. Okay, there's two laws of thermodynamics that you need to understand. You don't have to recite them word by word, but you need to understand what they're trying to encapsulate. So the first one is this one, the 0th law of thermodynamics, and it deals with thermal equilibrium. That is saying that two substances at different temperatures are mixed. The heat lost by one substance is equal to the heat gained by the other. If you think of yourself making a coffee or making some kind of hot drink, if it's too hot, you add a little bit of milk, a little bit of cold milk, and you stir it up. Both the heat of one and the coolness of the other cancel out, and they end up to be some kind of even temperature. They end up reaching a thermal equilibrium between them. Okay, yep. So that's the case. They always interact with each other. If you look at this example, you got a nail. Okay. Okay, yeah, here we go. Okay. Here we go. So yeah, you got a nail that's been heated. It's been thrown into the water. The kinetic energy of the particles in the nail are hitting the water particles, and they're transferring some of that energy. And what happens is eventually they'll reach a thermal equilibrium where the water will get a little bit warm, and then the nail will have the same temperature as the water it surrounds itself. against. The other one is the first law of thermodynamics, which is something that you've probably heard of, which is energy simply changes from one form to another, and the total energy in a system is constant. So this is considering a system that is perfect, that doesn't have anything that's taking away that energy in the form of sound or radiation. In this system, what happens is the nail transfers its energy to the water, and the water keeps that energy. The water doesn't lose any of that energy into the air, atmosphere, or the glass or anything. It's a perfectly closed system, right? And it's this idea that energy is transferred, that energy only exists in kinetic or potential form, and it's always being maintained in a system. But we know that's not the case. In reality, there's always energy that's being lost into the environment. So that's the first law of thermodynamics. Energy cannot be created nor destroyed. It's merely transferred or exchanged in one form or another. Okay, this is an important concept to understand. So this is called a heating curve. So I'll do an explanation, and I'll show you guys a simulation. Okay, but what this tries to do is explain what happens to temperature. Remembering that temperature is the average kinetic energy of particles. What happens to the average kinetic energy of particles as heat energy is added? So you can see, if you start off with a solid hunk of ice at minus 80 degrees and you start heating it, you start seeing that average kinetic energy of the particles or the temperature start to increase. It increases and increases. And then something happens once it gets to 0 degrees. It stays at 0 degrees. It doesn't increase at that point. It just stays at 0 degrees, and it's still absorbing energy because, look, you're still adding heat energy to it. So something's happening here. What's happening here is that the ice is being converted into water. So that water, icy little, mixture that's happening at this particular point, it's modeled to be all at 0 degrees until that ice is completely melted. Once that ice is completely melted at this point, then it starts to become completely liquid, and then it starts to heat up. You can see it starts to heat up again, and it continues heating up all the way up to 100 degrees. And what happens at 100 degrees? It can no longer stay at water at 100 degrees. It starts changing phase. It starts changing its state. And what happens is it starts to boil. So it's boiling, boiling, boiling until all the water has been boiled off and it all becomes steam. Now, this is suggesting that you got some kind of apparatus which is enclosing that water that's now a steam now, right? Because what happens is as you boil that water off in a kitchen, it just becomes steam and it evaporates, it goes somewhere else, it condenses, and then it becomes water again. But in this system, it's not. It actually is still in the container, in some kind of container that they got it, and they're adding more heat to it, and that steam is increasing in temperature. So you can see I've got the steam to 140 degrees. I don't know what temperature it is that steam no longer is steam, and it starts to break apart into hydrogen and oxygen, or anything like that. But I know for water, once you get past 100 degrees, it usually becomes steam. So have a look at this. From A to B, from there to there, it's warm ice. From B to C, we got ice melting. From C to D, we have warm water, right? That's what's happening there. And from D to E, we have boiling water. So we've got a liquid turning into a gas. From E to D, from E to D, if you were going backwards, what happens is you got a gas. Okay, sorry. That should be from E to gas to liquid. Yeah, from E to D, it's going backwards. So you can see the gas that is flying up here is starting to be cooled down. Energy is being taken away to it, and it's becoming a water again. But what happens is from E to F, you got superheated steam, and that's what's happening there. So these is what we call heating and cooling curves. So let's have a look at a simulation that's supposed to illustrate this a bit better. Okay. I think that sounds okay. So I'll narrate it. Okay, so we start off with some ice cubes. We get those ice cubes, we put them in a beaker, and what happens is we got this really nice crystalline or crystal structure where molecules of water are found in. So you can see it's -5 degrees. We presume that once we get to 0 degrees, those bonds will start to break and you get something a bit more loose in water. So we see that ice is going to break, and we can see the temperature is not increasing because we still have ice there, right? But once that ice is completely melted, now the water can be actually heated and you can get past that 0 degree point. And that's exactly what we see. But as we heat them up, you see those particles start to move. We've got it to 100 degrees. Now in the water state, these are still bonded together through their hydrogen atoms loosely connected to the oxygen atoms, but it no longer resembles that crystal structure that the ice had. These are more loose, right? Some energy has gone into breaking those solid crystal structure bonds into these loose, they call them hydrogen bond structures. Anyway, so the water is heated to 100 degrees. These bonds are no longer useful. They got too much energy, they break apart, and they start to be evaporated off, right? That those water atoms start to be evaporated off. They get so much energy that they leave, and you're left with nothing, or they're all just kind of floating around as a gas. Okay. Now that's going to be important because that ties with this. That's exactly what this is explaining here, right? Those situations. Which brings us to our next concept. In order to heat a substance from here to here or from there to there, you need to respect this idea of a specific heat of a substance. So the idea of specific heat is this. It's supposed to be this. Each substance, depending on what it is, requires a specific amount of energy added to increase its temperature by 1 degree Celsius. This is known as specific heat capacity. So you can look at some of these. I mean, if you think about it, the bigger the number, the difficult it is to increase its temperature. So if you had something like lead, just holding it with your hand, you could probably warm that lead up quite easily. But if you had something like water, you can see that just, putting a hot piece of metal into it is going to make little of difference to warm that water up because it requires a lot of energy to actually heat it up. That's just determined by the nature of the atoms that make the substance and how they are found bonded together in that substance. That's what it is. How much energy that's required to make those atoms which are bonded together move, right? We call that specific heat. And this is the expression. Now, we've come across these before. It's a difference. When there's always a difference between either temperature, distance, or energy or something, we usually represent it with this symbol delta, right? So here we got the energy added to a system is equal to the mass of the system. It's equal to the specific heat constant. So each one of those substances has a particular constant related to it, and it's equal to the change in temperature, right? The final temperature minus the initial temperature it was in. And that gives us the energy in that system. So let's have a look at an example here. Okay, in this example, we have 250 mils of water, and what happens is it's at 25 degrees Celsius, and they want to heat it up to 95 degrees Celsius. They want to know how much energy must be added to that. But it says here, sketch a heating curve for the water from 0 degrees to 100 degrees Celsius. So at 0 degrees, they presume that it's completely melted And now it's beginning to heat. It's completely in liquid form, and you can start to heat it up all the way to 100 degrees. And it tells you to sketch a graph, right? So you can just put, ball figure numbers. So you can say at the origin of the graph, you put a 0, and at where it reaches a plateau and it no longer moves, that's going to be 100. Okay, and you know somewhere before that it's going to be 95 degrees because you still haven't reached that 100-degree mark where it's going to boil off. You can put those values in. So you want to know that particular temperature, that particular energy that's required over this span of energy. So that's quite interesting. They're relating these Y values to these X values. And that in essence is what's happening in these graphs. I'm not going to be expected to for you guys to deal with the slopes of these graphs, but there's going to be a fair bit of work coming up with slopes in this next topic. But you can see the slope of this graph here is equal to the energy added here. You can see this one is flat line and it's a constant energy that's added. You can see that it doesn't have the energy term here. It does have a constant. This has got the specific heat. This one doesn't. This one's got latent heat. We use the symbol L, but here they've got the symbol of H. So you can see it's just a constant. It doesn't matter about the change in temperature because there's no change in temperature. It's just a constant that has to be considered to a specific mass and how much energy is required to melt it. Right? It just happens to be this energy here. Okay. So let's have a look at that. So we've got that. Now we've moved on to the second part. It says how much energy is needed to achieve this temperature change. So you start listing your values. You got 250 mils is equal to 0.25 kilograms. This is only for water. That's the beautiful thing about water. Whatever you have in milliliters is equal to, it resembles that which you would have in water. So 1 liter of water would equal 1 kilo of water. This is like saying milliliters is like milliliters is like saying grams, right? So you have 250 grams of water. With other substances, because the density is different to water, you can't treat it as that. So here we're lucky when we're dealing with water quantities, they just completely translate over. Anyways, you got 250 grams of 0.25 kilograms of water. Your final temperature is going to be 95 degrees. Your initial temperature is 25 degrees. If you look back at this, final minus initial, here gives us 70 degrees. And we got our constant, which is 4,200 joules. Sometimes they say 4.2 kilojoules, so be careful with that. But here we got the complete thing, 4,200 joules per kilogram Kelvin, so per kilogram, just per kilogram or per kilogram per degrees or per kilogram per kelvins. Both units are the same as long as you're using the appropriate temperature. So if I was using kelvins, it should be the same as long as I'm using either kelvins or degrees. Anyway, so I've got that. I know my equation. I substitute in my values and I solve for my value, and I find out that it's 7.35 times 10 to the power of 4 joules, which I need to add to this water to heat it from 25 degrees all the way up to 95 degrees. So that's specific heat. Okay, the other concept is latent heat. So this one deals with changing the phases of the substances. So if I want to go from ice to water, it's going to cost me some value. I got to add a certain amount of energy to it. If I want to go from water to ice, I have to take a certain amount of energy away from it. I have to make those loose bonds more compact and more rigid. If I want to make these tight, rigid bonds into something loose, I have to add more energy to them. If I want to make them into a gas, well, I have to add even more energy to it, right? You can look, I've got 80 calories here. A calorie is equal to 4,184 joules. If I want to make this liquid into a gas, you can see how much more. What is that? It's like almost just over 5 times, more than 5 times the amount of energy that I need to convert that ice into a liquid. Okay, so that's what we call latent heat. Latent heat is the energy released or absorbed during the change of state. So if I want to change from these different states, I have to either add more energy or I have to take away energy from it. And this expression is much more easier to understand. You have the heat energy added to the system, Q, is equal to the mass of that system, mass of the ice cube, mass of the water, the mass of the gas, multiplied by this constant, the latent heat of the material. Now this is, they're a bit different. So if you want to go from solid to liquid, there's a certain constant for it, and we call it the latent heat of fusion. And this one happens to be 334 kilojoules per kilogram. And if we want to go from a water to a gas, we have to add 2,300 kilojoules per kilogram, right? Now, if you want to go the other way, if I want to go from a liquid to a solid, then I'm going to have to take away that constant, right? And if I want to go from a vapor to a liquid, I have to take away that value. And I can take away that value by using some kind of heat sink, something that can take that energy away from those particles. So it might be, I don't know, it might be some kind of metal that I kind of blow this vapor through, and that vapor hits that metal and loses some of that kinetic energy onto the metal, and it condenses and becomes a liquid. There's different ways of doing it, but I got to leach out that energy to make it more compact, right? If I want to make them small. If I want to add more energy, then all I've got to do is just add heat somehow. Otherwise, if I want to make them into a water or an ice cube, I have to take that energy somewhere out. Now this flowchart really kind of drums it home. So you've got a solid, you're increasing the temperature of the solid. It gets to that state where you have to go through the latent heat of fusion. Some energy is added to change the state. Once it's a complete liquid, you can heat it up. Now you have to go through the latent heat of vaporization, where you change the liquid into a gas. Once it's into a gas, well, it stays as a gas until it becomes plasma or not, or you can go backwards, right? You take away the latent heat of vaporization, you condense it, it becomes a liquid, you cool it down, it becomes a liquid. You keep on cooling it, you have to go through the latent heat of fusion again. Once that energy has taken away to make those bonds more solid, you can then even cool down that solid even more until you get to what is known absolute zero. At absolute zero, those particles stop. They stop moving completely. Okay. Okay, here we got an example, nice and easy. So we got, given that the latent heat of fusion of water is 334 kilojoules per kilogram, how much energy is required to melt 250 grams of ice at 0 degrees to 0 degrees of water? So you don't have to worry about heating that water up. You just want to convert ice completely into water, right? If you had to heat that water up, you'd have to do a specific heat calculation on top of the latent heat calculation, right? So you'd have to do this one, plus that one. But in this instant, because it's still the same temperature, you're just changing state, you're just dealing with this equation here. So what are our unknowns? We know that the mass is 250 grams or 0.25 kilograms, SI units. And we know our constant, so we multiply those two together. So we figure out that it takes 83.5 kilojoules, or 83.5 times 10 to the power of 3 joules to convert that 250 mil block of ice to water. Okay. All right, moving on. So we've got another example. So this is an example where you do two calculations in one. So we have 50 mils of water is heated from a room temperature. So it's heated from the room temperature at 20 degrees to boiling point at 100 degrees. So I've had to add energy to boil that water to 100 degrees. Once I get to 100 degrees, I'm boiling it off. I'm changing its phase. So I'm going to have to do another calculation to see how much of that mass, how much of that 0.05 kilogram of water do I have to add energy for it to completely become a vapor, right? I'm not talking about hitting the vapor. I'm just converting it into a vapor, the water into a vapor. It is boiled at this temperature until it is completely evaporated. How much energy in total was required to raise the temperature and boil the water off? You've got two things that you've got to calculate. You've got to calculate its specific heat, getting from 20 to 100 degrees, and you've got to calculate how much energy is required to completely change it from a liquid to a gas. Okay. Now, this is a bit of a harder one because you've got to consider two. So you have two energies that you have to add. The total energy is equal to the specific heat of heating the water plus the heat of the latent heat of vapor of changing its phase from a water to a liquid. So let's do the first one. So we know 50 mils is equal to 0.05 kilograms of water. We know the constant is equal to the specific heat constant is equal to 4,200 joules per kilogram per Kelvin, or per kilogram per degree Celsius, let's say. And we know the equation. We know the mass. We know the constant. Now the change in the temperature is 100 minus 20. That gives us 80. And that's what we do here. So we got 0.05 times 4,200 times 80. That gives us 16,800 joules, right? And that's that energy just to heat it up to 100 degrees. You see, it's a lot of energy, right? So when you talk about like boiling water or heating up a pool, that's a lot of energy that is required to do that compared to something else, right? So you can see up here, back at our constants, you know, the next one up would be helium, right? Liquid helium. And to get liquid helium, there's a lot of energy you've got to take from it to actually get into liquid state. But you can see water is really up there, right? So when it comes to putting out fire, there's nothing better than water. Okay, so continuing on. So we've done our first calculation. Now we have to do our latent heat. So we got the mass, that's no problem. Now the constant is, it should be included here, is 2.25 times 10 to the power of 5 joules per kilogram. You can use this one, or you can use the one that I've given you here. Right? This one's 2.3, right? That's okay. Either one, I'll see that you've done the calculations and it should be fine. But I've also included them down here, I'm pretty sure. Yeah, latent heat, water, 2.3. Yeah, they've used 2.25. Yeah, it's about the same. That's all right. So that's the constant. So you multiply 0.05 by that constant. That gives you this value. It takes 112,500 joules to convert the ice, the 0.05 kilogram ice block into water. And now I have to tally up all the energy together, which is what I do here. And what I end up finding is my final total energy. It takes me all this amount of energy sorry, it wasn't a block of ice, to heat this water all the way up to 100 degrees and then boil it completely off. That's the amount of energy, joules. Okay, let's move on. Okay, so that leaves us to our last component here, which is the modes of transferring heat energy or heat, right? So you've got three modes. You've got conduction, you've got convection, and you've got radiation. So we've covered these before in year 10, but in this one, there's a particular calculation that you should be acquainted with, and it's this ability of the rate at which an object can conduct its energy through it. So you can see if you keep on heating this metal, in a perfect world, that heat would eventually heat the entire piece of metal up. But that's not the case because some of the heat is dissipated into the environment. So that's what this calculation is. So the thermal conductivity of an object is this. Is a constant that expresses how easily heat is transferred through it, right? So if you had something like metals, they tend to be good conductors of heat, so they'll have a high thermal conductivity. But if you had something like air or some kind of like organic material, like some kind of fiber, they tend to be low thermal conductivity, and they tend to have a low thermal conductivity constant. So, I mean, if you think about like a carpet, that's what a carpet is. It's stopping you from losing your energy, your heat energy on your foot, onto a tile or some kind of solid material. Because usually concrete or tile, they have a high conductivity and they take the heat energy through it quite quickly. But by adding an insulator to it, a thermal insulator to it, you prevent that from happening. They tend to have a very low thermal conductivity and take that energy less, and it's less efficient. Anyways, the expression is this. Thermal conductivity is given by this constant here, K. But this expression is thought of as the amount of energy that is taken by an object over a particular time. Now that T value sometimes can be just left here, but the expression is usually expressed as a ratio of the amount of energy taken per unit time. So what happens is Q is equal to energy, T is equal to time. Again, we've got a delta T. Remember, delta T has to do with the final temperature minus the initial temperature, or the temperature that's completely gone from one place to the next. So if this here is 50 degrees and on the other side is 20 degrees, then the differences will impact on this calculation. D is the distance between those 2 points, how far they're separated apart, and A has to do with the surface area where it's made contact. So if you've got your foot on a tile, well, the surface area would be equivalent to your foot, the area of your foot. If you had just some kind of circular spot, then that would be the area of that circular spot that you'd have to consider, right? Now, you're not going to be expected to do weird areas. That you might have to deal with rectangles, which is length times breadth, or you might have to squared, which is side squared, or you might have to have a circle, which is pi r squared. Okay, so let's move on. Okay, so here's a calculation. So we got the thermal conductivity of aluminium is 204 watts per meter per Kelvin. How much energy is transferred through a distance of 40 centimeter in a block of aluminium? A square cross-sectional area of 0.25 meters squared. So they don't want you to calculate the squared area of the square. They've given it to you, so it's pretty cool. With one side at 60 degrees and the other side being 10 degrees, if you apply the heat for 300 seconds. So they just want you to calculate the energy completely. So let's have a look at our unknowns. We know our constant, 204 watts per meter per Kelvin. We know our area, 0.25 meters squared. We know our change in temperature is going to be going from a nice warm 60 to a cool 10 degrees Celsius. And that's going to give me minus 50 degrees Celsius. The distance that they're spread apart is 0.4 meters. And the time I'm applying that heat for is 300 seconds. So I substitute my values in, I bring that T across, and I do that. So 300 seconds minus 204 value for my constant, multiplied by my area, which is 0.25 meters squared, multiplied by my temperature. Now, notice that it's a negative value. That negative value is very important. Don't neglect this negative value, because what that negative value is saying is that's the energy that's taken away, right? Anyway, so I divide that by 0.4, which is the distance between the 2 points, and I get this value. So I get 1,912,500 joules has to be taken away from the object that's heating it to the cooler place in order to get that heat across, right? And that's what that's saying there. Okay, let's move on. Okay, actually, before we move on, have a look at this. Now, remember our 0th law of thermodynamics, where an object reaches equilibrium. So you can see the final equilibrium point between the 2 places is not 60 degrees. So the other side doesn't end up being 60 degrees. The other side ends up being 50 degrees, right? So what happens is, in order for that to reach that certain thermal equilibrium between the 2 points over a specific amount of time, you're not going to reach that complete point because you've only done it for 300 seconds. You'd have to find the exact time that it will take you to reach that thermal equilibrium. But you can see that that change in temperature requires a certain amount of heat energy that you have to add to it. And it happens to be this value here. Okay, convection, just conceptually, I like this example of the summer days at the beach. But what you have to think about convection is the movement of, it's usually a gas or a liquid. You can't do a solid. So what happens is, if we think of it as a gas, as that gas becomes more enriched with energy as it's close to the surface, it heats up. When it heats up, it expands. As it expands, it becomes less dense. So it becomes less dense than the air in its environment, and it rises up. So those are the principles that we use for hot air balloons. We heat the air inside it, it becomes less dense, it becomes buoyant compared to the air in its environment. Anyways, as that air heats up and it makes its way to the top because of its density, what happens is you have some really nice cool air by the ocean, and what happens is that cool air kind of floods in and comes towards the mainland there, the shoreline, and occupies that space, and then that air starts to heat up and it makes its way up to the top. As that air that was initially moved up to the top is met by this other air that's pushing it up, that air gets even further and further away from the land, and it's receiving less heat. As it receives less heat, it cools down, it gets heavier, it becomes more dense, and then it makes its way back down where it heats up again and continues moving around. So we call that convection currents. If you think about magma at the center of the Earth and how it moves up and down, and it moves our plate tectonics, it's the same principle. It's being heated up, it becomes less dense, it floats to the top, it moves the rock as it's so far away from the core, it starts to cool down, it becomes more dense, and it makes its way back down. So we call that convection. It's usually related to liquids and gas. Okay, the last one is radiation. So this is quite interesting because what happens is anything that has matter in it should have some kind of energy signature that is released by it that can be interpreted as radiation. So you just standing there are releasing some radiation, and it's in the microwave range. So because you have a metabolism, because you're alive, because you have matter, your particles that make you up are oscillating, moving back and forth, and it's releasing radiation. And it just happens to be that radiation is in the microwave range. So anything between minus 272 degrees, minus 273 degrees is that microwave infrared. So you are infrared. So infrared radiation is what you release, not microwave. So you can see that's kind of the radiation that you release because you have a temperature of that. But if you were really hot stuff, then you could probably get to these temperatures over here. So stuff that you'd find in the sun, and you're releasing X-rays and ultraviolet rays. But because that's not the case, then that's what you are. Anyway, so what happens is, you know, it's a very important concept because, you know, we've spent a lot of time looking into this, because it is a question that I get quite often, which is, why is blue a hotter color? And this explains it, because what happens is when you heat matter up, it does release radiation, but that radiation is matched to the intensity of that heat that has caused that particle to move. So, you know, just jiggling a particle, you know, over some kind of small distance with a low amount of intensity is going to give you something with a very long wavelength, right? Something like a radio wave. So when you have electronics that move electrons back and forth, that's what you're doing. But when you have something like a sun or a star, which are just moving those electrons in a soup of plasma, I wouldn't say plasma, but a soup of, you know, broken atoms, you have, you know, some pretty intense movements in these particles, and you have these huge amounts of energy being released. So our sun, to our understanding, is a green sun. So around here, just a bit higher, our sun will be around here. So somewhere in between that will be the temperature of our sun. And what happens is, because that's what's happening there, that's kind of the peak wavelengths of radiation that's being released, and it just happens to be that is observable light. You know, you can also have, you know, you wouldn't have ultraviolet, but you have things. Yeah, you could probably have suns that are releasing light more in the blue and ultraviolet range. So that peak becomes more on this side. So that's got to do with how hot that object is. So if you heat anything up, it's bound to increase the radiation, the frequency, or sorry, the wavelength of the, sorry, it's supposed to decrease the wavelength and increase the frequency of the light that's being released by it. And well, that's radiation, right? It's the energy is being released in the form of this radiated light, and that radiated light is called photons. So that's another way that energy can be lost. It's a bit different to these other two. These tend to be, you know, either, you know, matter being swooshed around, or atoms being, you know, moved and smashed against different things. This one has to do with the release of energy in the form of particles that we call photons or radiation. And that's going to come up in your Year 12 course, but have a look at, you know, see if this can make sense. But yeah, so this curve is supposed to represent the average, you know, the most typical peak here is the highest intensity of a wavelength. So you can see this object at 600 kelvins, it's releasing the most strongest thing it releases is a wave a wave that's equal to about, you know, just under 500 under 5,000 under 5,000 wave units here. So what's that? That's equal to what's that? 5 times 10 to the power of -5 meters, right? So that's a really -5. Okay, no, that doesn't seem right. Okay. Yeah, no, that makes sense. Yep, -5. So somewhere around here, you can see it starts to get into the color range. I mean, it's less. So what's that, 4? Yeah, so somewhere around here. That's the main radiation that's being released, that color. Um, but it's also releasing a whole heap of infrared and red, and it's releasing a little bit of blue ultraviolet radiation. So even humans should have something. It'll be very flat line, and you can see that the wavelengths will be, you know, a bit larger, so it'll be more distributed towards this side. But everything has a signature of energy released. I mean, just exposing yourself to this curve, but just understand that radiation is that. It's just the electrons moving and releasing energy in the forms of photons is all you really need to understand about the concept of radiation at this point. Okay, excellent.